We are going to talk today about one of my favorite things, which, I have a lot of favorite things in math, but we're going to start chapter 9 here. And as you saw in the book, chapter 9, we're going to start going back to how to integrate things. So remember taking the antiderivative, right? Finding a function whose derivative is blah. So we've done this in the past. We've taken the antiderivative of x squared with respect to x, and we find that we get 1/3 x cubed plus c. But there's something interesting that comes up when we have something maybe like this. Okay, so I have something like this, x e to the x squared. The problem with this is, as you remember, and you've probably heard me not yell, strongly tell you that we can't distribute the integral across multiplication. What I mean by distribute is I can't integrate x and then integrate x to the e to the x squared, which we don't really even know how to do that, and then multiply them together. So this presents some sort of an issue for us right now, but don't worry, we're going to figure this out. So what we're going to do today is we're going to talk about this method of substitution. And where substitution comes from is, if you recall the chain rule, I'm sure you do. It's everybody's favorite. So if I take the derivative of a composition of functions, so I'm going to use capital F. Okay, remember what we do with the chain rule. We take the derivative of the outside, leaving the inside alone, and then we multiply by the derivative of the inside. Okay, and then a lot of times, remember from our previous discussions, we're gonna let little f of x, I'm gonna let big F, I'm gonna let little f of x equal the derivative of big F. So this will be f of, I'm gonna put little f of x, or f of g of x, excuse me. We used this notation when we first started talking about antiderivatives, right? So we have this chain rule, and basically what we're going to look at today is substitution is basically going to be undoing the result of a chain rule. Okay, so I want to undo, when I took the derivative, there are many ways that we can take the derivative, right? We can take it using the chain rule, the product rule, which we're going to talk about in 9.2, quotient rule, and all other sorts of things. So we want to look at, how would I find, is this the result? First of all, is something like this the result of a chain rule? And if it is the result of a chain rule, how can I undo it, right? How can I find the function whose derivative is x e to the x squared? So here's what substitution does for us, and I'm going to show you how I do this. And as always, because, math teacher, I want you to do what I say. I want you to do this the way that I'm explaining this in the video, and I want you to look at my notation. You should be watching my notation and trying to mimic how I do these problems. You should be using the same notation as me. You should be trying to copy the equal signs the way I do and really practice writing good mathematics. So what I want to do is I want to integrate this guy, right, to come back to something that was the result of the chain rule. So we know that this guy here, this big F, is the antiderivative of little f. I know that this guy, when I integrate this, would just come back to what I had taken the derivative of. But how to get that way, or how to figure out what that is, that's kind of the hard part. And this is where we do something called u-substitution. So here's what we're going to do. Now this is going to be a little cray-cray. My students tell me that cray-cray isn't cool anymore, and I should not be saying that, but that's okay. I'm also not 19, and so I'll do things that aren't cool anymore, and I'm all right with that. All right, so here's what we're going to do. This is why this rule is called substitution. What we're going to do is we're going to bring in this letter u, and u is going to help us rewrite this integral into something that I am able to take the antiderivative of. Maybe it's just an e, maybe it's a power rule, something easy to take the antiderivative of. So what I'm going to do is I'm going to let u equal g of x. Then that implies that if I took the derivative of this, du dx is g primed of x. So here's what we need to be able to do substitution. usually the inside kind of the function is going to be my u. And in order to be able to do substitution, what you must have is you must have its derivative sitting outside. I got to have the derivative of it. It can be off by a constant. That's the only thing it can be off by, a constant multiple. But once I do this, if you notice, if I kind of solve for du here, kind of hate to do that because the dx's, don't think of them as variables, they're differentials, but I can write it like this. I hope none of you lose sleep over that. I'm sure you won't. But look at what's going to happen here. This guy right here is going to be replaced with u, and then this whole thing right here is going to be replaced with du. So what I actually get is this guy right here becomes the integral of f of u du. And hopefully now this is an integral where I can take the antiderivative pretty easily. Maybe with the power rule, maybe it's an e, something pretty simple, okay? All right, you guys, so we're just going to do some of these. That is how you get good at this stuff, is you just do them. So I'm just going to do some examples for you. Hope that's going to be okay. Not that you really have a say in it, but I'm going to do some examples for you. So let's start off with that first example that I had given you. X e to the x squared dx. And if you remember, when we take the derivative of e and we use the chain rule, if you remember, what is the inside part? I know that's a little bit weird, but what is the inside part of e? It's the exponent. So what I'm going to do is I'm going to now notice how I write this. I write down here, I'm going to let u equal the exponent. And then what do I need? So if we go back to this layer right here, I know that I just made it mad. I know that du is equal to the derivative of whatever I set u to be times dx. This is a differential. You might remember this from Calculus 1 when we did differentials. But du then is 2x dx. Now come back up to your integral here and see, is this going to work? Do I have x dx in the derivative of u? I do have x dx in the derivative of u. I know you're like, but Sarah, there's a 2 there. Well, that little 2 I'm not very worried about. I'll deal with the 2 here in a moment. So let me show you what's going to technically happen. You'll get to where you're so good at this, you don't need to write this step right here. I'm just going to rewrite things a little bit here, and I want you to do this how I do this. I do not want your integral to have u's and x's in it at the same time. So if that's how you were taught in high school or something, or some other calculus class, you need to forget that and you need to do it how I do it. I don't want this integral to have more than one variable in it. It's a single integral, so it shouldn't have more than one variable in it. So look at what I want to get rid of. Well, I won't get rid of them. I just want to push them aside for a moment and then I'll come back. This x squared is going to be replaced, right, with u. And then if I keep looking at this, I want this x dx to be replaced by something. So what is this x dx going to be replaced by? Well, I want to isolate this x dx by itself. So all I need to do is divide by 2. And I get, what is x dx? X dx is 1/2 du. So this guy here is going to be replaced with 1/2 du. And then what is x squared going to be replaced with? U. Okay, so let me show you. So this becomes e to the u times 1/2 du. Again, why is it called substitution? Because we just substituted our x's for things in terms of u. So I love about mathematicians, if they call it substitution, it's because we're substituting. Now, why has this been beneficial for us? Because I can bring that 1/2 out. Now I have e to the u du. Now we're driving with respect to u here. So what is the antiderivative of e to the u with respect to u? It's just e to the u plus a c, right? So I'm going to add that c. So I have 1/2 e to the u plus c. That's great. That is I've gotten rid of the antiderivative. The substitution allowed me to find something that I can actually take the antiderivative of. And now the last thing is, what did this equation start off with? It started off with x's. So we need to come back and we need to rewrite what is u in terms of x. It's x squared. I don't know why I have that color. So I have 1/2 e to the x squared plus c. Okay, and of course, this is what's so great about taking the antiderivative. I could check. What would the derivative of 1/2 e to the x squared plus c be? Well, I would have 1/2, I would have e to the x squared times the derivative of the inside. There's my chain rule, people. Times the derivative of the inside. So I get the derivative of x squared is 2x, the c goes to 0, my 2's cancel, and all is right with the world. Well, maybe not, but all is right with mathematics right now, apparently, with what we're doing. I hope that makes sense. I want to do some more. Let's do a couple more. These are a good time. I think you're going to like them. I hope you like them. Granted, I'm just the messenger. I didn't actually come up with substitution, but let's look at something like this. 2x over x squared plus 1 to the 4th power dx. So, I mean, really, other than e to the x. Now, I don't want to say that this is always going to be true. You never want to say that as in mathematics, unless you're absolutely sure. But often, when you make your u substitution, often what you're going to let u be is this in the parentheses. Often, okay? Be careful there. I shouldn't say always, but often that's what it's going to be. Because if I rewrote this, this would be 2x x squared plus 1 to the negative 4. So remember, this was a result of a chain rule. So it makes sense that when we choose our u, it would be the inside. Remember whoa, sorry about that. Remember, the u is always the inside function. So sure enough, I'm going to let u equal x squared plus 1 in this case. Du then is 2x dx. You must write that dx there. If we don't have that dx there, then it's not going to cancel here. Now I'm going to just rewrite this one more time. You're not going to do this every time because you're going to get so good at this after watching my video that you won't need to. I'm humble as well. But this 2x dx, what is that going to be replaced with? Du, right? And then what is the x squared plus 1 going to be replaced with? It'll be replaced with u. And this is looking good. So how do I know this was going to work? Because I have, if u substitution is going to work, you need to have the derivative of u sitting there, nothing more than it, other than maybe you're off by a constant multiple. But if this, my friends, had been 2x plus 1 up here, I would not be able to use u substitution on this, okay? Because I don't just have a 2x. The derivative of u is 2x, not 2x plus 1. So in that case, we would have to do something different that's a little bit beyond this class. But if you ever want to take regular calculus with me, that's a good time. And in Calc 2, we get into that a little bit more. All right, so look at what we have. I have u to the negative 4 du. Am I able to integrate that? I am. I can use the power rule, right? So I'm going to add 1. That would be negative 3 and divide by it, plus c. And then what do I have? My final answer, right? I'd probably write this as a negative 1 over, so this 3 stays in the bottom. And then what is u? U is x squared plus 1. And then this to the negative 3 will just give me a 3 on the bottom, plus c. And we're done. Isn't that cool? I love these. I just think they're so much fun. I know that if you've been watching my videos at all, I know that probably does not really surprise you. Okay, so that was fun, but weren't you a little bored? I was a little bored. Well, not bored. I never get bored by these things, but I want to show you one that's kind of an interesting one that that we don't really think about very much. Let's say I have 4 minus the natural log of x all over x dx. This one can be a little bit tricky, but let's look at our options for u, right? I mean, what are our options for u? I guess I could let u equal 1 over x, but the derivative of that is like a negative 1 over x squared, and I don't have an x squared there. What if I let u be the inside, right? Because if I rewrite this, if this was 4 minus the natural log of x to the 1/2, again, what we end up seeing is what is the inside function, right? Remember, again, this is the result of a chain rule. So what is the inside function? My inside function in this case is 4 minus the natural log of x. Okay, so I take the derivative. The derivative of 4 is 0. The derivative of natural log of x is 1 over x dx. Do I have a 1 over x? Yeah. Ooh, oh, I forgot my dx. Oh my goodness. You guys, I bet you were like screaming at the computer. Maybe not. You probably don't care that much. But remember, algebra is the hardest part sometimes of calculus. It is very true. So if I ever say it's just algebra, you should like call me and tell me never to say that again, because algebra can be tough. Look I can rewrite this like this. That's just simple. Again, I just did it. That's some algebra. That can be difficult if you don't see it. So look I do have a 1 over x. Now, I don't have a negative 1 over x, right? So what do I want to solve for? I want to solve for what I do have. I have a 1 over x dx. So I'm going to solve for that. I get a negative du equals 1 over x dx. Okay, I'm going to put a line here. So what do we get? That negative, I'm just going to actually throw in front. I know it's with the du, but that's just a negative 1. What happens here? This guy right here is going to be replaced with u raised to the 1/2, and then the 1 over x dx just becomes du. Isn't that pretty? I just love this method. It's just so cool that you can get this integral that is so much more simple just by doing a simple u substitution. I kind of feel bad for u because u does all the work and then doesn't really get any of the glory, because when we come back to the final answer, right, there's no u involved. Poor u. But this is my final answer. So I took the antiderivative, I added 1, divided by that, and then my last step, of course, your answer should not be left in terms of u. My last step then is to replace it. All right, people, I want to do one more and then that's it. I know, I could be here all day, but I actually have to go to a meeting, so I probably can't sit here all day. This one can be a little bit tricky. What if I had 1 over 3 minus 5x dx? I know this looks a little bit strange. You're like, but Sarah, I don't really see a chain rule involved here. Now, I don't want to really, I guess I don't have to do this, but I want to show you why this is going to work out okay. I'm going to put this as 3 minus 5x to the negative 1, making sure I put parentheses around that whole thing. And if I do that, I hope you can see what your u is going to be. That kind of helps you see the chain rule maybe, or see the composition, not the chain rule, but the composition. So I'm going to let u be 3 minus 5x. So what is du? It's a negative 5, right? That's the derivative of this guy. And remember, we just tack on a dx there. But look at what I want to get substituted here. This is going to become u. What do I have left over? I have just dx. So I need to get dx by itself. So to get it by itself, I'm just going to divide by a negative 5. So what is dx going to be replaced with? Negative 1/5 du. So this dx right here is replaced with this whole thing. I just always bring the constants and throw them in front. And I get u to the negative 1 du. Now, if you try and do the power rule with this, remember you add 1 and then divide by the result. Well, if I add 1 to negative 1, I get 0, obviously, and then I can't divide by 0. So remember, that should kind of make you think, oh, hey, wait a minute. There's something else to this, right? I remember trying to do the power rule with things like this before and it not working. And so what we do then is I'm going to rewrite it as 1 over u, and then we just saw before, what is the derivative of 1 over the stuff, right? Or the antiderivative, it's the natural log of it. So I'm going to have the natural log, remember, absolute value of u plus c, okay? And then my final answer here is a negative 1/5 natural log, absolute value, 3 minus 5x plus c, and we're done. And of course, remember, you can check yourself. As I say in my face-to-face classes, check yourself before you wreck yourself. I know that's so silly, but it's fun. Take the derivative of this, negative 1/5. What's the derivative of natural log? 1 over the stuff times the derivative of the stuff. What is the derivative of the stuff? Negative 5. C goes to 0. So what do we have here? These negatives, 5's cancel. Then I get 1 over 3 minus 5x, And I know this is cheesy, but I think that deserves a smiley face, don't you? I think so. I like that when I talk to you guys, I imagine you're talking back to me. I'm not sure if that's healthy or not, but I enjoy doing these videos. I think they're pretty fun. So I hope you've enjoyed this as well. Practice, practice, practice. That is how you get good at u-substitution. I mean, really in mathematics, that's how you get good at anything. Do your suggested, do the fun sheets. If you need more problems for practice, if you want more fun, all you have to do is send me an email and I'm happy to do that for you. All right, you guys, have fun.